Okay, let's start our course. Okay, last time we did the linear approximation. Okay. Okay, so I will review a little bit linear approximations. Actually, we also did the exponential growth and decay, but I think you should be able to do it. The exponential and decay is like the p0 and e, and you have some kt. Okay, the idea is this is just initial. Okay, this is your base. Okay, in nature, it's always e, Euler. K is a constant, the growth rate constant. T is the it can be hour, seconds, depends on the size. Okay, so exponential growth and decay. It can be also used for the radioactive. So we can look for how the mass of the substance gets reduced. Okay. I hope you understand the concept. Okay. Basically, what you need is just this relations. Okay. You have the total size is equal the initial size, a constant, multiplied by e with the power of kt. And when you want to derive, you get the rate of change. Okay, you can get the dp dt, and you get the another constant in the front from k and p0 e, and also another k and t. Okay. And we can count many ways as long as the models they can multiply by themselves. Okay. Like a populations in human, bacteria, animals, most population using this formula. Okay. Also, in some physics phenomenon, you can also approach with the E. Okay? Okay, so I will just skip the exponential growth and decay, and we go for the linear approximations. Okay. So what we did before in linear approximation, I'm just reviewing a little bit. Okay. So we need to find a function. Okay. We need to find a function. So let x. Okay. Let x is unknown. Okay. Or we want to know this, right? Our step is by looking at this limit definition of the first derivative. Okay. Where the at the at number a, you have a tangent. You have a tangent line. Okay? You have a tangent line, and the definition of that tangent line is by limit. The first derivative is if limit approaching x, x approaching a is equal to this formula. Okay. So what we are doing is actually we have okay. So let this is the curve of f of the functions. Okay. Just make it f of x. Okay. Or maybe it will be clearer if I want to calculate some x here. Okay. So let's say this is the f of x. Let this just a general function. Right? And to help us calculate the x, okay, the fx, we need another reference. Okay, let's say we have a here. By doing so, I can approach, okay? I can approach with this A. As A is getting closer, maybe A is here, or maybe here. There will be another tangent here. This is A1, A2. Or maybe just the A on the left. To simply see what we are doing, okay? So if A known, okay, or this is our reference point. If this is our reference point, meaning the A is easy number that we can calculate, okay, then we can see that the curve and the tangent line at the close point from X to A is similar. Okay, so maybe the one is the curve like this, and the tangent is this. Okay, so here the red color, the straight line, when it's getting zoomed into the observations, we see that the curve is getting straightened. Okay, it's getting similar to tangent line. So we can say that our f prime of A is actually just the difference in functions and x. Okay. Please wait a moment. Putar aja dulu. Dah. Dah. Okay, so we can approximate the f prime A with the difference in the f and x. Okay, so what you can see here is this triangle. Okay? This is delta f. This is or this triangle. This is delta x. This is x a, or I will write this is the distance x minus a, and this is the fx minus fa. Okay. And a is, you can also see a, you can take from left or right, it doesn't matter, as long as your calculation is correct. Okay, the minus positive is all correct. It doesn't matter. Okay, you can take a any points that you think it can be reference. It can be a reference. Okay, okay, that's linear approximations. Okay, and the other one is we call the Newton's method. Okay, Newton's method, the same formula, but we make the f of x equal to 0, because in Newton's method, the purpose is we need to find the real solutions for the real roots. Okay, so when you have the f prime a, the fx is 0, so you have this this expression. Okay, so you change the variable, then it will be this. Okay, x minus a is or approximating negative of f of a divided by the f prime of a. What we need to find is the x, and a is another reference. Okay, this is reference. Okay. And for Newton's method, you can find x, the new x, as many times as you want. Okay? So you can get closer and closer to get the x. So what really is you have a graph. Okay? Okay, you want to find the when f of x is 0, which is the crossing point. Okay? You want to find here, okay, this red dot here. You want to find this point. Okay, but you don't really know what that point is. Okay, and maybe you can think some number aside from that red dot. Let's say we have the uh, this point here. Let's say this is x naught. We are approaching x naught to the curve, and then we are make a tangent line, making a tangent line, okay, and it's crossing this. So I will make this is x1. Okay, as you can see, x1 is getting closer to our red dot. Okay, and you can make it closer if you want. Uh, maybe it's around here. Let me make smaller. Maybe it's around here, and this is, yeah, it's getting closer and closer and closer. Okay, depends on the situations, what error you need. Okay, like what number decimals behind the decimals, how many numbers you need. You can do it as many times as you want, and it will be getting closer. And maybe the answer, the x maybe will be something a number 0.00001 or 0004. The more zero, meaning the error is minimum. It's good. Okay? If you have any database, maybe in your project in the future, maybe you have some research based on finding numbers or computational works. If you have find like 000 something, meaning it's getting closer to the exact value that you want to approach. Okay? Meaning if you design any software or any computational programming, and you can decode to make the error as minimum as you can, then you are successful. Okay, to find estimating value as exact as the truth. Okay, so this is a good approach. I will going back the Newton's method later in after several chapter 4. Okay. But let's just move on to chapter 4. Nick. Okay. Any questions from the linear approximation? Okay, before we are entering our chapter 4, let me briefly introduce you to, I think you already have in physics. You have the usually S, okay, for the position. Okay. Uh, let's say we have some specific functions of t. let's say this is a positions. I think in physics, you can derive and you get velocity, derive, you get accelerations, right? So let me write some questions for you and see if you get idea from these questions. Find average velocity and average speed if t is from 0 to 5. Okay. So do you know the difference between average velocity and average speed? Okay. Let me write the definition for you. Okay. I'm not sure. Have you learned in physics? Like find velocity, right? You have learned. Okay, so average velocity, okay. This is by definition is change in position and change in time. Okay, this is average velocity. And average speed by definition is total distance travel total time. Do you understand what it means? Okay, so okay, average velocity, it only care the first point and the finish point. The change in the 0 point and t time after some t. But the average speed is the actual distance traveled. The total distance traveled is not equivalent or is not equal with change in position. Okay. Okay. So I think we can get easily the average velocity. So average velocity by the definitions is just s at t at the endpoint is 5, okay, from the information, and the initial point is when t is 0, okay, and the time is just 5 minus 0, it's just 5. Okay. So we can look up the S5, okay. S5 is 5 cubed minus 6, 5 squared plus, okay. And S0, I think it's easy, it's 0. So 5 cubed, 125, 25, 150, right? 150, 125, negative 25. So this is 20. Okay. So 20 and 0. So average velocity is just 20 divided by 5. It's 4 meters per second. Oh, I haven't said that it's in seconds and position in meters. Okay, so you get the average velocity. Let me copy this whole functions. Okay, let's now look at the average speed. Is total distance traveled and total time. Okay, how we solve this problem? How you can find the total distance traveled? Okay, imagine the person is going with the functions. Okay, it's going to some place from t0 t5. Okay, we need to make sure how is his movements. Okay, how he moves. Okay, is it just straightforward like that, or maybe he just running back and then move forward? Okay, that we need to actually find. Okay? Okay, can you find or can you guess how we deal with this total distance traveled? Any idea? Graph? Uh-huh. Yeah, graph is correct, but why you need to find the area on the graph? Mm-hmm. The graph is correct, but mm, but not area, not area. Okay, okay. Let me give you a just random curve. Okay. Uh, let's say this is the positions. Okay. Yeah. Okay. Something like that. Okay. Yeah, maybe just like this. Okay. Um, if this is positions, okay, this is the uh, time and position. What is the tangent line in each point means? Velocity, right? Okay. So we define our velocity by this, right? So we see from here, this point is this tangent. And in this point, the second one is, so it's getting horizontal. Okay, get it? And at some point, okay, maybe here, maybe it's horizontal. And after horizontal, it will be, so this is still positive, right? The gradient. And maybe around here is 0, right? But after that, it's going negative, okay? Right? You get the idea? Okay. Now, we have our own functions s, okay? And when the gradient change, okay, from positive to negative, it decided by this 0, right? So if we can find when the gradient is 0, we can predict this positive negative, right? So let's try to find the first derivative, okay, from here. So ds over dt is 3t squared minus 12t plus 9. Okay, and then let's make 3t squared minus 12t plus 9 is equal 0. So t squared minus 4t plus 3. So t minus 1, t minus 3, right? So this means when t equal 1 and when t equal 3, okay, there will be a turning point. Okay? This is turning point. Or we also say this is stationary. Or we also say this is critical. I think in your textbook it's critical. Critical number or point. Okay. So what the critical means, okay? What the critical means. So if you imagine the person is maybe he is starting some 0, and then he moves until t equal 1. When t equal 1, maybe he moves back. Okay? And then after t equal 3, he's going forward again. Okay. So let me give you the so t equal 1, t equal 3. So we already count the S5 is 20, right? S0 is 0. Let's check S1 is check with the 1 minus 6 plus 9. It's 4. And S3 is 27. This 27, 27. It's 54. It's 0, right? Okay. So meaning when t equal 3, the person back in 0. Okay, back in 0. Okay. So let me draw. It's 0. Let's say this is 20. And let me make this is t equals 0. This is t equals 5. Okay. The final and the initial point. Okay. Maybe this is a person. Okay. And then he moves. Okay. He moves to t equal 1. T equal 1 is 4. Let me make 4 here. Okay. So this is t equal 1. Okay. So he moves. Okay. But then at t equal 3, he backs here. So he going back. So he's back at the initial positions. After 3, he's moved forward. Okay. Maybe he's running. So from 0 to 4, he plus 4, right? And then also plus 4 again, because he's going back to 0, and plus 20. And this is the total distance traveled. Okay. So total distance traveled is total distance is 28 divided by total time is 5. So this is 5.6 meter per second. Okay. So by introducing this average speed, okay, also in your course physics, okay, by introducing this the total distance traveled, you see that it's not always the case that if you have a functions, you are just doing fine. No, but sometimes in the functions, you will see maybe you will go back and then move forwards. Okay? And the important point in this case is this turning point. Okay, this t equal 1, this t equal 3. This is important, key important point in the chapter 4. Okay, in the chapter 4, in when we are dealing with the graphs. Okay? At this point, this critical, we say critical point, okay, or number. This is important. Okay? Okay. Any questions from this example? Actually, this is physics, but I hope it can give you some insight. Okay. Okay. Now uh, let's move on. Okay. Let's start our chapter 4. Okay. So chapter 3 ends with the linear approximations. Okay. I will not go for, there's one chapter, one section in chapter 3 is called hyperbolic functions, but I will skip it because actually the difference between hyperbolic and the trigonometry in terms of applications is the same because they have the same property, but they have different definition. But I will skip it for now. If we have time, maybe I can visit the hyperbolic functions. But let's move on to chapter 4. And actually, I plan to give you another examples for related rates, but I will give that examples maybe next Monday. Okay. So now we're just going for chapter 4. So chapter 4, okay. In your textbook, it will start with the extreme theorem or the maximum and minimum. And after that, we get the mean value theorem. But for our course, I will start with the second one first, the mean value theorem, because you will see why I'm telling you the mean value term and then extreme value. Okay. Okay. Let's start with the mean value theorem. Okay. Mean meaning at the middle ground. Okay. You have something to the right, something to the left. Mean is somewhere in between that right and left, but it's not in the center, not really in the center, as long as it's in the between of left and right. Okay. Okay. So suppose, okay, suppose you have functions that uh, continuous uh, at this interval, and the functions also differentiable at this interval. I hope you get the idea why I'm writing A, B different. Okay. Continuous meaning it's including, you can see the function is not having any hole. Okay. Differentiable meaning the function need to be differentiable. If the functions at the end, of course you cannot differentiate that functions, right? Because it's like at the pointy one, you cannot differentiate it. Okay. Okay. It said that there exists C in those interval where the average rate of change equals to instant rate of change. Okay. Instant rate of change meaning the tangent line. Okay. Remember, okay, the tangent line, or this is the tangent. And A is less than C is less than B. So what is the average rate of change? Okay. So the tangent is the first derivative, right? So the first derivative of C is equal, okay? Okay. Is it similar to our linear approximations formula? Similar, right? Yeah, that's why I'm trying to go here first, because it has similarity with our linear approximation. Okay, so the whole calculus, okay, the first calculus is all connected. Okay? It's all connected. And if you understand the concept, the basic concept, and how you connect with each sections in the calculus, you will see that you don't really need memorize much, okay? Because you can always derive some functions from other formula, okay? So see here, okay? So what does it really mean? Okay. Let me give you how we get the idea of this formula works, or how we see in the visual. Okay. So let's say we have a graph. Maybe the graph looks like this. Okay. You have a 2-point. Okay. Let's say this is the A, f of A. This is B. Okay. Because we are dealing with the A and B, the endpoint of our interval. Okay. The interval AB. Okay. The average rate of change in this interval is the endpoint to the left and endpoint to the right. We connect with one line. So this is the average rate of change. Okay, this blue one. So this blue one is so average rate of change is FP minus FA divided P minus A. Okay, got it? Okay. Now, to prove this, let's draw line parallel with the average rate of change. I will draw maybe here. Let's say this is parallel to the that line. Okay. And also I'm drawing here, so that I can prove that this formula can be approached with any from anywhere. Okay, you can approach this formula from anywhere. So okay, so see the red color line. Okay, the dashed line. Okay, imagine this line you can move. Okay, okay, let's move this parallel line and make it at least touching one point of the curve. Okay, and also moving this line, the upper one, at least touching to that one point in the curve. Okay, when you are doing this, okay, then this is actually what C is really mean. So you have C, you have C. Okay? You have many C actually. It's not always one C. It can be many. It depends on the function. So at that point, you see the line is the same, right? The gradient is the same. So you can say this is actually true. Okay? This is one way to prove the formula through the graph. Okay? So you can approach and prove the formula through the graph. Okay? So this is true. Okay? But when you have maybe a point or the curve like this, you will have a trouble here, right? So it will be ruining your formula. It won't be acceptable. Okay? So you cannot approach with the pointy like that. So you need to have differentiable, like the beginning, the assumptions. Okay? The function needs to be continuous and differentiable. Okay? Okay, based on this f prime, okay, based on the first derivative, as a consequences, and also for the next theorem, we will have the f prime if the f prime is greater than 0. We say the function is increasing. When the function is less, when the first derivative is less, the function is decreasing. And if the f prime is 0, then f is a constant. And you can say also critical number gets open, but this one, I would say it's a constant. Okay, it's a constant. And also, from the mean value theorem, you can also prove some mathematical nodes, functions. Maybe you want to prove, is it true that sine x is always less than x? You can use this formula to prove that. Or if it is the tangent x always greater than x at some interval. Is it true? Okay. So you can also prove something like that, some function. I will show you how. But before that, let me show you. Okay, I will write the formula one more time here. Okay, this formula. I will rewrite and change the some form. Okay, let me write this is f prime c b minus a. Okay, and let's write in terms of f of b. So I can write f of b is f of a plus okay. Okay, notice that you see the similarity with our linear approximation before, right? But there will be a difference, but I will tell you later. But here, okay, see if A is less than B, okay, then I can say that based on our assumptions, let's say that B minus A is always positive. Let's say that B minus S is positive, okay, here. So what I'm doing here is, if you see the formula, okay, if B minus A is always positive and FBFA is always a constant, always a fixed number, then the one that deciding how the value will be, is it minus plus positive, it will be F prime, right? Okay. So let's say this is always positive. The B minus A is always positive. It's always positive. So if the F prime C is positive, okay, then here you can say FB is greater than FA. Okay. And when F prime C less than 0, it's negative, right? And negative positive, it will be negative, right? So FA is, of course, okay. And when the F prime is 0, then you can say FB is FA, right? So based on these tools, okay, you may have many expressions, okay, from the functions. You can have random functions, maybe quadratic, polynomial, trigonometric functions, and you want to prove some arguments in mathematics. You can always using this mean value theorem as long as at least you get either A or B. either A or B, at least one. You can still use this formula, at least one. I will going back explaining this tools later, but let me write some notes about the linear approximation and what the real difference between the linear approximation and this mean value term. Okay, because in terms of the formula and expressions, both are very similar, right? Okay, let me write the comparison with the linear approximation. Okay, um, we have the delta f delta x. In linear approximation, it's approximating, right? And in mean value term, this is precisely equal. So this is in linear approximation. This is in mean value term. Yeah. And the concept, okay, in linear approximations, if we are dealing with the same A, B, okay, B should be closer or nearby A. And our B minus A is delta X. And in this case, our C is in between of A and B, okay, in between. It doesn't need to be near, okay? Not necessary for A to be near B. That's difference, okay? And let me write the expressions one more time here. F prime C. Let me write this is FB minus FA divided by B minus A. Okay, based on our case, the average velocity and average speed, okay? The mean value theorem, this is in the middle ground, right? So you may have, this is F prime, you may have the maximum F prime at some point, okay? And you may have minimum F prime, okay? And A is between some C, some and B, okay? So you may think that the mean value term is like this case, okay? Like the runner, okay? You may have the maximum speed and minimum speed, but you may always have the average at the between of the maximum and minimum, okay? And also, let me write the average speed, okay, to give you the notes. This is max, minimum. In mean value theorem, the average speed is actually what? It's actually approximating the initial speed. Okay, this is MPT, this is LA. So maybe okay, in some cases, okay, you get the idea that, oh, okay, it's the same number. But in actual definitions, it's not always the case. Okay, so our linear approximations, imagine the average speed that the runner has. Okay, in linear approximation, what we are really doing is we are just making approximation through his initial speed, which initial speed is the instant velocity. Okay, we see that our instant velocity from previous case is the average rate of change is 4. the average speed is actually 5.6. It's a little bit different, right? Okay. I hope you get the idea. Let me move on to the how to prove. Okay. Okay. So this is a comparison, and then uh, uh, I will write MVT how to prove some math statement. Okay, let me start with the if I have e to the x is greater than 1 plus x, okay, and x is greater than 0. Prove that the e to the x is always greater than 1 plus x. Okay, I will show you how. Okay, so how to prove? So prove let fx. So we state our functions first. Okay, we state our function first. Let's state the functions e to the x. Let me write this, and it's or let me make this is greater than 0. Okay, and because it starts with x should be positive, right? X is greater than 0. Let me check. Okay, let me check when x is 0. Just checking. Okay, because 0 is easy number that we can compute. So f0 will be e to the 0 minus 1 plus 0. This is 1 minus 1. It's 0, right? It's 0. Okay, let's check our first derivative of fx. The first derivative is e to the x is just e to the x, right? Minus, you have 1 plus x. Derive, it's only 1. Okay? So minus, I will write this as 0. So you get the whole concept. Okay. So your f prime is actually just this. And this is actually positive, right? Because x is positive, right? When x is 0, it's 0, right? But x should be positive. So it will be never negative, right? It will be never less than 0. Get it? Because x is always positive, the statement of e to the x minus 1 is always correct, right? It's always correct that it is always positive, right? So this will be always positive, right? And this statement here is actually our part of our equation. So we are writing back the whole equation minus 1 plus x greater 0. So no matter how you are rewrite your formula, okay, this part, this always positive, right? And no matter what, okay, this will be true, okay, right? Because this is always positive, then e to the x. Okay, so the statement is ended true. Okay, so what we are actually doing is remember that we have the fb and then fa plus f prime c b minus a. This is actually what we are doing. So we are just looking at the f prime and make sure what is the f prime. Is it always positive? When f prime is always positive, then fb is always greater than fa. And then our functions here is always positive. Okay? Okay. And then let's try the formula. The next statement. Let's say we have e to the x. I will make this with the beautiful conclusions. Okay, it's greater than 1 plus x plus x squared over 2. So is it true or not? Yeah. So the first thing we need to do is let our functions. Let's say our function is gx. This is e to the x minus the whole 1 plus x squared over 2. This is greater than 0. Okay. And then this is the same. X is always positive. So try 0, okay, to check the all 0, 0. And this will be rendering the functions to be 0. Okay. And check the g prime x. This become e to the x minus 1 becomes 0 plus 1 plus x, right? Okay. And uh, because x is positive, whatever number x you put into the g prime is always positive, right? Meaning the functions is increasing, right? G is increasing. Okay? And then because the whole part of this function, this g prime, is also the same as this one, okay? The first original functions. We can also say that gx is greater than g0, okay? Or if you remember, the fb greater than fa, okay? So that you can say that, bring back the original statement, this is always true. By the way, these expressions um, can be this is 6. This is can be written like this, and it will be until infinity. And e to the x always greater than all of those. Okay. You can write this in another terms. This factorial. And we will not going to discuss more about these terms, but these terms will be in calculus too. When you are learning the Taylor series, series and sequence, okay, you will learn something similar to this expression. Okay, this is just how we can approach, okay, e to the x with some expressions, okay? And then we are seeing that with our tools, the mean value theorem, we can prove some inequality. We can prove some mathematical statement if they have some number that, or some interval, or you can guessing some interval and making the statement, proving the statement whether it's correct or no. Okay. Okay. Another example is It's a direct example. So let me write the example for you. So if the functions 1 plus at the interval interval 2 to 9, okay? So you need to find all number C, okay, in this interval where the C is basically our mean value term, the C from mean value term. So this is quite a direct approach. What you need to do is just calculating the functions, calculating the the derivative, substituting the number, and looking for C. So we can start with finding the derivative first. So 1 plus let me write the functions 1 plus x minus 1, 1 over 3. So this 1/3 x minus 1. This is minus, okay. Or I can write this 3. But if you get like rational expressions in your derivatives, okay, the meaning of the denominator, if x minus 1, so you can write f is differentiable except at x equal 1. This is just notes, okay, not related to the questions, okay. But if you need to observe what is really happening, okay, you can always look for the denominator first if you have the rational functions. And then we just compute, okay, when f is 9. I think when f is 9, 9 minus 1 is 8. 8 becomes 2. So it will be 3 minus 2. So it's 1 over 7, right? So the tangent value is 1 over 7. So what we are doing now is just looking for the C here is equal 1 over 7 and find the C from this expression. So 1 over, let me write this, and moving the 3 to here, and it's still 3, then and I will write C minus 1 squared, and this becomes this. And after we are cube, we are square root both of them. So C minus 1. Do I need positive, negative? Should I write positive, negative after we square it? Or no? No, right? Okay, I think you know. Okay, why I just need the positive one? Because our interval is from 2 to 9. Only positive. Okay, so negative, we can just skip the negative one. So this is 7, right? And our C will be 1 plus this whole thing. Okay, notice that because in exam, you don't need the calculator. So you don't really need to calculate in decimal point. Okay, just writing like that is fine. When you have log, just write maybe log 2 or ln3, ln4, maybe ln4 over 5, and then square root. That's fine. That's fine. Do not calculate until the decimals. Okay? No need. It's not mathematical. It's not calculus. Okay. Okay. Another case, another example with the mean value theorem. So this is example to find C, and all is direct approach. You just need to put the number in and calculate with the formula. Okay. Another example is if you have the value, okay, and you don't really need the whole functions, okay, and you have given all the value of the functions, the derivative. Okay, so you have the value of functions at some point. You have the derivatives, at least the amount. Okay, the question is how small can the f of 4 possibly be? So first, do you understand the questions? Okay, do you understand the questions? So you have interval 1 until 4, from 1 to 4. You have the minimum derivative, the minimum derivative. So the derivative should be at least 2, right, from the information. And you have f of 1 is 10, and it's asking f of 4. So how small? Okay, so the smallest f prime x is 2, right? And on the interval, this interval from 1 to 4, we can apply our mean value theorem. Okay, and so our f4 minus f1 should be 3 times f prime c, right? And f4 should be f1 plus 3 f prime c. Okay? And we get the idea that f prime c, the smallest number of the derivatives is 2. So the smallest f of 4 is just the f1 is 10 plus 3 and 2, 16. So smallest number of f4 is 16. Okay. However, the questions, okay, these typical questions, is quite direct approach, but sometimes it can be, it can have many variations. Okay, so as long as you understand how you deal with the notations, how you deal with the questions, I think it should be not a problem. Okay, and the idea is always using the mean value theorem. So if you have interval, you have function, and you have the derivatives, you can relate all with the mean value theorem. Okay, similar to these questions, I have another typical question. So suppose 3, so you have some interval in the f prime. This is for all x. I show that Okay, so suppose you have f prime in between 3 and 5 for all x, and show that the difference between f8 and f2 is between 18 and 30. So this is also typical in mean value theorem, and I think it's also it can be straightforward, and you can have a direct approach. Okay. So you see that in the first sentence you have the f prime, and in the last sentence you have the f some number and minus f some number. Okay. So of course it is really obvious, right? It's really obvious. You can see that this is, you can make it fb minus fa, and that will be f prime c. Okay. You can start from bottom and going to the top, or from the top to bottom. At least you show that both of this is or having relations. Okay. And when you are proving that, then it's you already show that, okay, this is actually true. Okay. Okay, you start with the mean value term. Okay, and let me write this as fb minus fa is f prime, and then let a is 2 and b is 8 based on our observations. So f8 minus f2 is f prime c is 6, or let me write 6, just 6 f prime c. Okay. So you have also this f prime x is 3 and 5. Because f8 minus f2 is 6 times of f prime. Let's multiply by 6. And this will be, and it will be true that okay. Okay, another I think last example for the mean value theorem. Uh, show that for 0, okay, show that for from 0 to pi over 2, the interval, tangent x is greater than x. Okay. I already show in the first case the inequality. So you can use the inequality. Uh, you can use tangent x minus x greater than 0, or just using tangent x as the functions. That should be fine because the right side is only x. Okay. And x is positive in between 0 and pi over 2. So notice that the interval is not include the equal, because when equal pi/2 tangent will be undefined, right? It has. Okay, can you try this one? Can you solve this based on mean value theorem? Can you try to solve it? Okay, try to solve it. Mhm. How you solve it? Using pi/2? Pi/2, of course, you cannot use the. Okay, so okay, to prove statement in math, okay, if you have the interval, um, proving some statement is not necessarily you need to plug in the number to the function. What you need to do is you are proving that with all number that can be in between the interval, it is true, unless you want to point each or every point in that statement. So you need to have like general statement which is all true, okay, which is all true. You get the idea? Yeah. Yes. 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 Yeah. Differentiate. Yes. Yes. Confused. Okay. Is it the new editions? Oh, it's seven, right? Seven, right? No, no. I mean, no matter Chinese or English, as long as the editions are correct, you need to make sure the the title, the chapters. The difference is only the order, all the same. Yeah, all the same, but different order. Okay. Yes, yes, yes. Correct. Yeah, correct. Yeah. Okay. We can write let the or let me rewrite the functions from here. Okay. So fp is fa plus f prime c b minus a. Okay. And the a is less than c less than b. Okay. To make sure that we are really doing or approaching the correct interval, let me write another terms x. Okay. This is actually just b, but I want to make sure that we are really correct. Yes, we know that if we put in b to the functions, it will be having infinite, right? Or let's say this is pi over 2. Okay. But actually, if you just write the first one, it's actually okay. This is just to make sure the safety. Okay, this is just to make sure. Okay. So let's uh, let make let the functions let our functions maybe minus x like that. It should be greater than 0. And if we have derivative, the tangent will be what? What's derivative of tangent? Secant squared. Okay, secant squared. And what will you do in the exam if you forget what is the derivative of tangent x? What will happen? Depressed? No, no. Don't be depressed. If you forget, remember you have, okay, and derive and using the quotient rule. What will happen if you don't remember the quotient rule? Depressed. uh, actually, I always forget the quotient rule. F prime G minus G prime F. Is it F prime G or G prime F that minus? Because if you missing positive and negative, your calculation will be incorrect, right? So what I remember is the product rule. The product rule. So you have dx. This is fg, right? And make sure the first one you write is f prime g. So in product rule is plus g prime f. And when you write the quotient rule, write the same similar thing, but minus, and then define g squared. Okay. At least it will be minimize your effort, right? You don't need to have like loading or for the information you need to store in your brain. Okay. Because sometimes if you are really memorizing through some functions in your brain, it's like external hard drive. When you plug in, okay, I remember. But when you are remove that hard drive, okay, everything removed. Okay, I don't remember anything. Okay, make it like your internal hard drive. Okay, so you don't really need like high storage, right, for your internal hard drive. Usually, your internal hard drive is lower, right? Low, it's low. So make minimum effort to memorize. Okay. Be lazy but smart. Okay. Be lazy but smart. When I was still in your age, I also lazy, but I have my own way to be smart. Be that students. Okay. That will be cool. You can eat, sleep in any course that I teach, but it doesn't matter as long as you understand. Okay. Because every school, I think, in Asia, it's still having really conventional or traditional way. So the teacher will, oh, blah, 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 giving you information and you will like, oh, too much, too much, too much, right? So sometimes, I know that sometimes you need to rest. Sometimes you need to, okay, I need to have more relax. That's also uh, um, I respect that. Okay, I respect that. So don't worry if you want to have like you want to eat, maybe you watch some YouTube, maybe a funny YouTube video, but do it like just like maybe 5 or 10 or 10 minutes. It's okay. In my course, it's okay. as long as you don't make noise. Okay, that's I appreciate. Okay, because I also a student, so I know how you feel. Okay, so back to this example. So secant squared x minus 1 is greater than 0. Okay. So what will you do from this expression? So you have now secant squared. Okay. Now you need to use some knowledge or some information from trigonometry. Okay. So you need to have a good basic trigonometry to solve this. Okay. So in trigonometry, okay, your secant x is actually 1 over cos. And cosine, okay, so sine and cosine is actually really basic in trigonometry because all the relevant trigonometry idea is came from sine and cosine. Okay, sine and cosine is pretty basic. Maybe if I have time, I can explain why it's called sine and cosine. Okay, it's actually meaning like a curve. Like if you have a bow, okay, like this is a bow for archery, for arrow and bow. You have a string, right? This is the blue one is the string. When you pull the string, it will make this line. And they create a formula from this shape to define the angle and the line. It was in ancient India, the first time trigonometry found in India. Okay, and it's translated to Arabic and then translated to Latin. And maybe in Latin you say sen, right? And in Latin, sen, right? You call sen, right? Yeah. What is the definition? It's curve, right? Yeah. Okay. Okay. Sine and cos. Okay. Based on the sine and cos, okay, you need to have a good basic trigonometry. What I mean is, if you have cosine, when you are 0, it's 1, right? And when you're pi over 2, it's 0. So it should be like this. Okay. So whenever you have 0 and pi over 2, so your cos, let's say x is, or in this case, cos c is always less than 1, right? When you have 1 over cos c, is always greater than 1, right? So this part is always greater than 1. That's why this is always positive. That's why it's true that tangent x is greater than x. Okay. So every inequality that you can think of or you can find in the exercise, you can approach with this kind of process. Okay, you can approach from the derivative. Okay, I have proved that if you have a, b, and c at the middle c will be a dominant factor. It's dominant factor to make sure that if this is negative, then it will change the whole concept. Okay. Sometimes you need to prove whether it's true, and sometimes you also need to prove whether it's incorrect. Yeah, but using the same concept, Okay. Okay, I think I will stop here. Okay, I will stop here because the next one is the new section, the maximum minimum theorem, the extreme value. I will stop here to give you some moment to think, and maybe if you have questions, you can ask the questions. Do you have any questions? I think for proofing, you get the idea how to prove. Okay, is that okay? Okay. And remember, okay, be lazy but smart. Okay, be lazy but smart. Okay. Okay.